Parliament's Research Center in Brussels, but as a disclaimer, I'm speaking here like on a personal capacity, and those are my private views and opinions. So what I'm going to talk about is, first of all, clarify what is meant by circular economy, then look at how energy is being used in the linear economy and in the circular economy, then give an overview of the of some studies that were done on the impact of the circular economy on energy use and on greenhouse gas emissions, and then finally some conclusions. But before I start, I want to say why this matters. And I think for having sustainable and low carbon development, there are three big issues, three big fields, three big transformations. The first is the energy transformation towards a renewable and sustainable energy system dealing with energy. The second is dealing with materials and resources. That is the circular economy that tries to have a more sustainable use of resources in the economy. And the third one is the natural world, so the field of agriculture, land use, and biodiversity. And all of these three big areas, of course, interact with each other. For example, the circular economy and the natural world, you have things like bio-based materials, and in the interaction in this triangle between energy and land use agriculture, you have things like biofuels, and also the idea of having bioenergy with carbon capture and storage, which would address both energy needs and reducing greenhouse gas emissions or reducing greenhouse gas concentrations at the same time. What I want to focus on here is the relation between the first two, the energy and the circular economy. So energy and resources. Some definitions. The idea of the circular economy is to keep resources in use as long as possible and extract the maximum value from them while they're in use, and then afterwards, instead of throwing them away, recover them and regenerate products and materials at the end of each service life. Related to that is the concept of resource efficiency, which has been defined as using the Earth's limited resources in a sustainable manner while minimizing the impacts on the environment, which means you create more with less and deliver greater value with less input. As a measure of that, you have the resource productivity, which is defined by Eurostat, the European Statistical Agency, as the gross domestic product divided by domestic material consumptions. So how many euros of GDP do you get out of a kilogram of materials? And that measure can of course be criticized because it goes just by the mass of the material but doesn't take into account the scarcity or the value of them. And there's a report by the European Science Academies that looks at different possible indicators for the circular economy. But this is the one that's used in the official statistics. And finally, of course, renewable energy, it's often regarded as part of the circular economy because the use of fossil and nuclear energy resources which you burn is by definition a non-circular activity. There are some related concepts, cradle-to-cradle resource circulation, which are more or less the same as the circular economy. There's the field of industrial ecology, which looks at how materials flow through industrial production processes. Then there's the idea of a service economy in which you do not anymore own the things that provide a service, but you pay directly for the service. So for the example being, instead of owning a car, you use Uber, or instead of, you just use services instead of buying materials, of buying products. The sharing economy is also related to that, like things like car sharing or Airbnb, where you rent an apartment that someone else is not using at the moment. And related to the service economy is the also concept of product as a service. This is the famous diagram from the Arthur Magellan Foundation about what a circular economy looks like. And it has two sides. This green side here, which is the biological materials and the biosphere, and the blue side, which is minerals and industrial materials. And so up here you have resources, which you don't see, resources which are extracted, and then this goes to parts manufacturer, product manufacturer, service provider, and to the consumer, who can use this all over again. And then on the biological side, you recycle or regenerate it to put it back into the production process. Some of it can be used for energy, as in the form of biogas. And on the blue side, on the product side, first of all you can prolong the useful life of a product by maintaining it, repairing it, and then reusing it, redistributing it, sharing it, or reuse it and redistribute it and make new products out of it, or in the end recycle it to recover the materials. Now, just a few words about what's going on at the moment with circular economy. One big player, of course, is China, which is the biggest user of resources in the world. And the focus in China is on industrial cycles, to make sure that the Chinese industries get the materials that they need. Started in 2008 with a law on the promotion of the circular economy. It is a national development strategy in the 12th five-year plan since 2011, and also in the current 5-year plan. There's a national strategy for achieving a circular economy, and there are 13 industrial parks in a pilot program where one company tries to use as much as possible the waste materials from the processes of other companies. The European Union also has a program which is focused more on resource efficiency and waste reduction. It consists of a circular economy action plan called Closing the Loop, a set of targets for reducing the waste, a strategy for plastics in a circular economy, and it has also set up a stakeholder platform, held various conferences. Now, how does all of that relate to energy? This is an idealized view of the so-called linear economy, which essentially goes from resources and uses them in products, and then they end up as waste. So the model is also called take, make, use, dispose. And it starts from resource extraction, where of course you have the energy used from mining, drilling, or farming, if you're talking about bio-based resources. Then the transport of the materials to the manufacturer. And I put this bracket here just to indicate that there's a supply chain. So you have various stages of transport and manufacturing to go from the mineral resource to the raw material to components to finally end consumer products, which of course all needs energy, the transport and the manufacturing obviously. Then the distribution, where energy goes into warehousing, shipping, retail outlets. The use, which is mostly energy using products like cars and electrical appliances, but it might also be things like building materials and insulation materials, which in the end influence how much energy your building will use. And in the end, there's the disposal, and of course, you already, like, this linear economy doesn't really exist because you always have recycling, you have some reuse, but the circular economy tries to make that much more a guiding principle and eliminate waste and resource extraction as much as possible. So in the circular economy, I'll speed up. You have much the same things, and then you have also, these loops that go back, energy associated with collection and disassembling products for reuse. Just some useful numbers. Mining makes up about 11% of energy use, and recycling of aluminium and steel reduces energy use by quite a lot and is already done quite extensively. And we have the converse thing of resources being used for energy, but that was discussed yesterday. It's not the focus of this presentation. Now, in order to see how the circular economy would impact on energy use, I had a look at various studies, all of which try to give some answer, but I found that, first of all, some use quite an extensive definition of circular economy and include also the energy transformation, renewable energy, energy efficiency. And I found that none of the studies really do single out the impact of circular economy on energy use, although they do state the impact on greenhouse gas emissions, which result to a large extent from energy use. So the energy impact must be somewhere in the data, but this data is not easily accessible. First thing I looked at was something from the Center for European Policy Studies, which looked at various studies and also warned that they're different to compare because they're using different approaches, different assumptions. The European Commission estimates that circular economy could reduce greenhouse gas emissions by 450 million tons per year, so that's about a 10% reduction, but also does not publish figures on energy use. Then we have the UNEP International Resource Panel, which also says greenhouse gas emissions could be reduced by 15 to 20% with more resource efficiency. But that combining with energy transformation gives much larger percentages, like 2/3. I looked at a study from Ecofis, but that was problematic because that also includes the energy efficiency and renewable energies. Then a study from the Ellen MacArthur Foundation, which has the same problem, includes renewables and energy efficiency. Finally, a study from Deloitte, which really aims to look at the impact of recirculating materials and products, and finds savings between 13 and 66% for the various sectors, most potential in vehicles and electronic equipment. Then we have the Club of Rome, which for which a study was done, which studied different countries, and it also has sectoral results in which just the material efficiency just cut the carbon emissions from 3 to 10%, of which I suppose most is due to energy savings, but we don't get that information from the study. Okay, I'll speed up. Now the last question is, what does it mean overall? Of course, if you go to full resource efficiency, full recycling, your energy use from mining will go up, but that for the other things not necessarily. So in the end, I think the more you go to the end, it might also go up. Question is, what's the objective of the whole thing? Is it to minimize energy use? Is it to minimize the use of critical resources? Is it to minimize greenhouse gas? Or is it to maximize social long-term well-being? Okay, then there are, well, interactions and limitations. I may leave these to the questions. And just the conclusions: moving toward a circular economy is expected to result in a reduction in energy use, but from the studies we cannot tell by how much. So that would be an interesting thing to study. And it seems that from the studies that climate and energy benefits do not follow automatically from implementing a circular economy. So it would be good to consider them in designing circular economy approaches. And better modeling of and understanding of the relationship would be useful, but it could also be good to just go ahead and do things and then see what the results are.
Thank you. So we're kind of running out of time, so maybe we have time for 1 or 2 questions. 2, and that's it. And Nicolas can get prepared.
Yes.
In the circular economy, as such, the industrial circular economy, the one you presented on the right, the blue one,
Yes.
You are still using energy. So perhaps you are using less energy and it's more efficient than the linear economy as you presented. But you are still in a process of using energy. On the other side, the green part, which is a biomass cycle, you are producing energy potentially. In this circle, and even you are, I think, producing entropy, because you are lowering the level of entropy of the system and you are able to produce energy and entropy through the cycle of biomass, which is a combination and integration of many cycles. The cycle of CO2, the cycle of water, the cycle of nitrogen, the cycle of other ingredient in the... So in my opinion, the only true circular economy is a circular economy of biomass, and thanks to photosynthesis. So in order to improve that, which can be a goal, not only to spend less energy, but to produce energy, we need to improve the photosynthesis in the future. What do you think about that?
We'll take the second question and then you decide
yes.
how you answer.
In the model I presented, the production circle is a Carnot cycle, and the linear cycle you're talking about is like pulling in gasoline, then heating it up, burning it, and then disposing of it. This is a linear thing, whereas in a steam engine, you have the full cycle and you leave the steam in this engine. So this is a circular thing, and then there you don't lose, and you even gain energy again in this cycle. So this is a full Carnot cycle, and this would of course be more energy efficient and you don't lose as much material. So this, I think, corresponds to my model here. And I haven't looked into it any further, but maybe it's interesting to discuss this.
Okay, I think for the second question, yeah, but you would indeed to get in this cycle to go from the material that you've used now, that you have in your product, to get that back into the production. You of course you need to put in energy again. So, and but the energy doesn't stay inside the material; stays inside the cycle, but the useful energy does of course not. Okay, let's take this offline. And the biomaterials, bioenergy, of course, has a lot of potential. But as we saw yesterday, I think we'll still need things like metals and silicon to do a lot of the products and services that we need in our economy. But it's an interesting field of development.
Okay. Very short comment with no answer.
Okay, so it will be a comment with no answer. When matter is concerned, very often the matter which goes through circular economy is of lower quality than at the entrance. So that means that most of the time you are going to use more of it for the same function. If you want to have it at the same higher quality, that means that you need to purify it, which is usually very costly in energy. So there is a systematic analysis of these various issues and the relative weight, industrial weight of each of these situations in terms of matter circular economy.
That's a discussion for lunch. Now we have Nicolas Raillard, who is leading a group within the SHIFT project about mobility, which is one of the big issue. So maybe you'll present yourself more.
So yeah, hello everybody. Well, actually, I didn't lead that project. Francesco Luciano did, so an expert in mobility, but I was his assistant, and so I'm here to present the results and the modeling of that work. And I want to give this special focus on modeling because you're experts in models and scenarios, so maybe I'll have interesting feedbacks. So our subject was low carbon daily mobility in French medium density areas. Here is a bit of context for France. So on the right, you have the CO2 emissions per sector in France, and as you can see, the transportation and especially the road transportation is the biggest emitters of CO2. It accounts for 39% of the French CO2 emissions. That is 126 megatons of CO2 per year. When you take a look just at transportation, you can see that daily mobility accounts for approximately 60% of the emissions, and you have 20% for long distance and 20% for transporting goods. And we have an objective with the National Low Carbon Strategy for France and for transportation of reducing by 29% the emissions of transport by 2028 compared to year 2013. Now when you look specifically at daily mobility and traffic being the number of kilometers traveled by cars, here you have the amount of kilometers traveled by cars per week in different kinds of areas in France. So on the right you have the dense urban areas, Paris and the close suburbs of Paris. And then the tallest bars represent the peripheries of conurbations, French conurbations. And the far left bar is rural areas. So what you can see is that the peripheral areas actually travel a bit more kilometers than rural areas because they are attracted by the center of the conurbation, especially for going to work. So this is why we focused on these kind of areas. So the purpose of the project was to propose short and medium-term actions to reduce carbon emissions from daily mobility in those medium density areas, and to try to quantitatively evaluate the effects of the proposed solutions, which was the originality of the project. The perimeter of our study, so within the perimeter is on the left, and what was out of scope is on the right. To make it clear, so we are dealing about people mobility and not freight. We are dealing about this daily mobility, which is defined in France as mobility remaining within a radius of 80 kilometers from your home. So we are not talking about long distance. So daily mobility is typically going to the groceries, going to visit your aunt, going to pick up your children at school, and so on, going to work, of course. We focused on intermediate density areas, which is in between dense cities and pure countryside, pure rural areas. And the study was about short to medium term, so we limited our study to a time frame of 10 years. So we needed to evaluate the effects of our solutions within this time frame of 10 years. As we started the study in 2016, the 10-year time frame was the end date of the study was 2026. We focused mainly on CO2 emissions. It was just about France, and we studied a few promising domains of actions. Not all possible domains of action, so the study was not meant to be exhaustive. First, about these medium density areas, here is how we defined this zone. So the basic unit of our rezoning was commune. So the commune are the smallest administrative division in France. And communes are categorized by our National Statistic Institute into different categories. So you can categorize by the size of the conurbation the commune belongs to, and you can categorize according to where in the conurbation the city is located. So it can be the center city of the conurbation, which is the last column on the right. It can be cities just around it, still in dense urban areas, which are called suburbs. Then it can be outside of the urban pole, but still close to the urban pole, and it will be called polarized communes. And if you go even further, it's rural communes. And the medium density areas are the orange cells. So you can see that you have center cities of small conurbations, you have suburbs of small to medium conurbations, and you have polarized communes of big and medium conurbations. And when you draw it on a map, it gives the purple areas around cities. So dense areas are in pink and rural areas in green. Those medium density areas represent 11% of the French surface territory. In terms of inhabitants, it's 43% of mainland France. That is 27 million inhabitants, and the average density of those areas is 450 inhabitants per square kilometers, which you have to compare to the average in France of 120 inhabitants per square kilometers. And if you take the average for Île-de-France, the region containing Paris, it's 1,000 inhabitants per square kilometers. So here are the promising domains of actions that we wanted to evaluate. They are not like innovative or whatever, but that was the first time an evaluation was performed for those medium density areas. So we studied telework, we studied grocery delivery at home, we studied bike system, express public transportation, and ride sharing, and I'm going to explain a bit those different terms shortly. But first, a few words about our methodology. So for each of the domains of actions, we first led a state-of-the-art study in order to find out about the different trends within each domain of actions. And then we fixed a specific mobility system within this domain of actions. So for example, for telework, you have many ways to organize a telework system. You can say, okay, on telework day, everybody stays at home and that's it. Or you can also build some telecenters and tell people you can go to whichever telecenter you want or stay at home. And you have many ways to organize telework. So we fixed one particular system, and this system being fixed, we try to imagine how behaviors, mobility behaviors, would evolve with this new offer. Having done a hypothesis about the behaviors, we then estimated the CO2 emissions associated with these new mobility behaviors, and on that purpose we used the model called iMove, which was designed by the Research and Development Department at EDF. And there was another branch to estimate the expenses involved by implementing the specific mobility system that we imagine, but I'm just going to talk about CO2 emissions today. So that was a prospective kind of study, so we had to imagine what would happen in 10 years, but we started on year 2008 because this is the year we have a lot of data about mobility in France, because the French state organizes like a big poll every 10 to 15 years about the sociology of people and the mobility of people. So we have a big database on that year, and the EDF model was calibrated on that year. That's why we start at 2008. So we first had to define a reference scenario and then alternative scenarios, and all the results I'm going to present are actually at year 2026, and there are comparisons between the alternative scenarios and the reference scenario. So I'm now describing the hypothesis for this reference scenario. So we have data from the National Statistics Institute about demographics. So between year 2008 and 2026, there is a 8% increase in population for medium density areas. About mobility, there is just an increase of 3% of kilometers traveled by people, because there is an aging of the population, and people, when they retire, they travel less for their daily mobility because they don't go to work anymore. The car stock increases by 8%, so approximately like the population, and the structure of the car stock evolves. So you have the arrival of electric vehicles in dark blue at the top, of hybrid rechargeable vehicles in yellow, and you have diesel and gasoline that are the tendencies are inverting because of a new fiscality in France on diesel and gasoline. So when you then compute from this car stock the unitary emission, that is the emissions when one car travels 1 kilometer, these they decrease, and when you agglomerate all the mobility, taking into account the slight increase of mobility, there is a decrease of around 20% of CO2 emissions in the reference scenario. So now about the alternative scenarios that we evaluated. There were two kinds of alternative scenarios for the different domains of actions. The first kind were the ambitious scenarios, in which we imagined that the mobility system was fully implemented within 10 years and fully efficient. So for example, for carpooling, you would have like several carpooling stations with parking for bikes and for cars, so that you can easily share rides, and you would have a nice national app to share your rides, for example. So a good offer, and then we imagined in this system how behaviors would evolve. And then we had those maximal potential scenarios, in which we imagined that there was still this offer, this good offer, but a constraint on car. Whatever the constraint is, it can be a carbon tax or a reduction of space for cars. And these scenarios were, the goal of these scenarios was to estimate the maximum reduction in CO2 emissions that you could get with the domain of action which is evaluated. Okay, so here is, once you have the behaviors, we needed to compute the CO2 emissions. And we used a model developed by EDF. So here is how it works. the model is actually based on a photo, a snapshot of French mobility and sociology in 2008. So we have a precise cartography of people. So people are categorized in 270 categories, depending on the revenue of the household, the structure of the household. So is it couple with one child, two children, single family with one child, or things like that. Where they live, so in medium density areas, dense areas, their social professional category, and do they have a car or not. And each category of individual will generate each year a certain amount of trips, and the trips are categorized in 70 categories. So according to the motive of the trip, so going to the groceries, going to the restaurant, whatever, and the distance of the trip. Once you have this, you can have different modes. So the next module is about how the trip is performed. So you have the modal share. So is it performed more by car or by bus or by train? The type of road that is used, if it's a road mode. So is it a rural road or is it in a dense area? And the occupancy rate of the vehicle. And with all those information, you can use the emission factors of either the modes that are not cars, and the simplifying assumption here is that the emission factors are constant over the 10 years. And for cars, there is a stock simulation. So every year you have a renewal of old cars, and so new cars are entering the stock, so that the structure of the stock evolves with hypothesis on the new stock. Into a bit more detail, so if you imagine that you have the individual types along lines, you have the trip types along columns. So let's take type I. So let's imagine it's a craftsman living in a second decile household, living in medium density areas. They have 2 cars, and this is a couple with 1 child. These type of individuals will generate trips over the year. And let's consider type J, which is going to the groceries between at a distance between 7 to 20 kilometers. Then here we will have some information. We will have the number of person kilometer generated per capita and per year, and we'll have the average modal share. So like, for example, here 95% by car, and the rest by train or bus. And you will also have the average occupancy rate and which kind of road is used. And then knowing that, you can deduce the CO2 emissions for 1 person per year for this type of trips. Then you know the demographics, so you know how many people you have in this individual type. You can then compute the CO2 emissions for this type of trip for the whole population of type I of individuals. And then when you sum up all the cells of this table, you have the aggregate CO2 emissions for France. Okay, now let's start with telework and see what are the hypotheses and results using this model. So here our hypothesis, the system we imagined for telework is that you have telecenters pretty much everywhere, so that people can go either by foot or by bike to a nearby place in order to work, or they can stay at home. Our maximal potential hypothesis were that 47% of the jobs could be teleworked and 2 days a week. So when you multiply both figures, it leads to a decrease of around 20% of passenger kilometers traveled for going to work. For the ambitious scenario, we figured out that it would be easier for larger companies to organize telework and a bit less easy for smaller companies to organize it. So we assume that 30% of the jobs within large companies would be teleworked and only 10% for smaller companies. And those teleworked jobs would be teleworked 1 day per week. So when you know the structure of companies in France, you can compute that it leads to a 5% decrease in passenger kilometers for going to work. And when you feed those information into the iMove model, so the model by EDF, you get this reduction in CO2 emissions. So for the max potential, it's around 5% CO2 emission reduction and around 1% for the ambitious scenario. As the EDF model was kind of complex to explain, we figured out that it would be good to find an easy way to explain the results. So here is an explanation just for the maximum potential scenario. What I did here is just take year 2008, where we have the data, and try to see what would happen if in 2008 the telework system was already implemented, and just compare without and with the telework system. So what you can see here, I represented traffic at year 2008, that is kilometers traveled by cars, and the daily commute work accounts for around 30% of the kilometers traveled by cars. So with telework, you just act on this share of mobility. And then we said that half of the jobs could not be teleworked. This is the orange, so these trips do not change. And 3 days out of 5 of the week, you don't telework. So this gray part is still performed by car. And the remaining part in yellow is actually the traffic which will be avoided thanks to telework. And this is 6%. In medium density areas, CO2 emissions are accounted by car for more than 95%. So when you reduce car traffic by 10%, you reduce CO2 emissions by 10% also. So here 6% reduction of traffic leads to 6% reduction in CO2 emissions. And so we find back the order of magnitude of 5%. There is a slight difference between 2000, because between 2008 and 2026 there is an aging of the population, so this share of work decreases slightly, so it explains that you only get 5% in the end. Now grocery deliveries, so I present here one system that we proposed, and which is delivery rounds. So basically you replace all the trips to go to supermarkets or hypermarkets by delivery rounds to each household. There is a trick with French statistics because the grocery shopping includes also window shopping kind of thing, so more like big malls where you go just window shopping. So we got rid of these trips. And then we needed to assess the efficiency of delivery rounds compared to everybody going to the groceries. So what I did is a Monte Carlo kind of simulation. So Monte Carlo simulations are randomly drawing situations and then computing results and like studying the distribution of results and try to get information. Why is it interesting to do it in that case? It's because it's very difficult to find data about like every supermarket in medium density areas. So here I just draw average situations and hoping that the results will also average nicely. What's important here is to have the right distances to supermarket, and the distances that are randomly drawn are actually the distances that are measured in average in medium density areas to go to supermarkets. So I draw this random situation and then I imagine delivery rounds, which is the figure on the right, and then I compare the distances traveled by all the cars to go to the supermarket, which is at the center of the figure, and the distance traveled by the delivery vehicles. And I can plot the ratio, so the efficiency ratio of one compared to the other. So if you have 10 here, it means that you have to travel 10 times less kilometers thanks to the delivery round compared to the car system where everybody goes to the groceries. In order to use these curves, you need to know how many trips you replace, because the more trips you replace, the more efficient the delivery round is. So you need to know approximately how many people are going to the supermarkets in medium density areas per day, and you need to know how long you wait before delivering the groceries, because the longer you wait, the more people you will have to deliver. If you just wait 1 hour, you will have maybe 2 customers to deliver. If you wait 3 days, many customers will accumulate over time. So the assumption we took is that the grocery deliveries will just come to your house once every 3 days. So this is, the summary of the methodology, and the final result is that these delivery rounds actually decreased by 78% the vehicle kilometers traveled for supermarket trips. When you fit this into the iMove model, it leads to a reduction of 9%, just the left bar, of 9% in CO2 emissions. Why? Because you just act on 11% of the traffic, on the traffic. Okay, let's go through bike system. For the bike system, we imagine a very nice bike system with bicycle lanes along all roads between the towns, and within towns you would have speed limits of 20 or 30 kilometers per hour, so that cars and bikes can nicely cohabitate. And we also imagine that the households were fully equipped with vehicles that look like bikes, but maybe are not bikes. So for example, what I represented on the left is like speed pedelecs, which are actually bikes with no, so they are assisted electrically, but there is no cap on their speed, so that you can easily go at 40 kilometers per hour. And this is not considered as a bike according to European legislation, even if when you look at it, it really looks like a bike. We imagine that household would also have, if they need them, cargo bikes or trailers in order to carry groceries or to carry people. So in this system, we imagined for the max potential scenario that trips longer than 20 kilometers could not be performed by bike. We also imagine that long trip chains, so a trip chain is when you go to one motive, so for example to work, and you don't directly go back to your home. So for example, you go to the groceries before going back. And we imagine that if this trip chain was more than 40 kilometers total, you could not do it by bike. When you have things to carry, we imagine that if the distance to travel is more than 7 kilometers, you cannot do it by bike. And if it's lower than 7 kilometers, it depends on the volume of groceries and the number of people you want to carry. For the ambitious scenarios, we actually asked experts to estimate, according to different kind of trips, the probability that people would use a bike or not within 10 years. So we had them fill a form like that with trip motives according to lines, with a type of people like social professional category of people along columns, and within we had also a third dimension, the distance of the trip, so between 0 to 3 kilometers, 3 to 7, and 7 to 15. So by giving this form, we implicitly assume that trips more than 15 kilometers could not be performed by bike in the ambitious scenario. And then we asked experts to give marks between 0 to 5 according to the probability they felt about the different kind of trips. And then we fed it in the iMove model, and here are the results. So the max potential scenario leads to a 33% decrease in CO2 emissions, and the ambitious to a 15% reduction in CO2 emissions, which is large. The main drivers of these results is that actually in medium density areas there are still a lot of short trips, plus we had this speed pedelec bike which enables you to go to 20 kilometers, so you can cover actually a pretty large number of trips. When you want to explain the results, if you look at the mobility at your 2008, you can categorize mobility according to the trip, to the distance of the trip. So the left bar here represents the total number of passenger kilometers, of person kilometers during one whole year on trips that are between 20 to 80 kilometers. Then you have the same for 7 to 20 kilometers and on the left, it's trips less than 7 kilometers. So what we said for the max potential scenario is that all the trips greater than 20 kilometers could not be performed by bike. So we get rid of them, and they are still performed by car, bus, etc. For trips between 7 to 20 kilometers, we get rid of trips where you have to carry people. So this is the yellow. You get rid of trips when you have to carry goods. So this is the gray part. And you get rid of too long chain trips, which is the orange part, and you just keep the green part at the top. For trips lower than 7 kilometers, you can also carry goods or persons if there is if the goods are not too voluminous or not too many people, and it represents the dark blue part. And now when you plot this along a pie chart, you get the 34% mobility, which corresponds to the 33% that we get with the iMove model. So we get back on our feet with just looking at year 2008. Now let's go to express public transportation. So what is this concept? The concept is the public transportation going from the peripheral areas of a conurbation to the city center, not directly necessarily to the city center, but at least to an intermodal pole in which you can interconnect with urban modes. So you can have trains like RER or Transilien in Île-de-France, or you can have buses that take the highways, and they are going fast because they just have like 4 to 5 stops maximum, and the stops are optimized so that the bus doesn't have to get out of the highway in order to pick up people. So this is the concept. Now we needed, I don't know if you can read it, we needed to estimate the amount of mobility that could be cut by this type of public transportation in order to compute in a second time the CO2 emissions. We based our data only at year 2008 here. So what the mobility we kept was, of course, daily mobility. It's the focus of our study. And we just kept working day peak hours mobility. So we tried to catch the mobility at times where most people live, so that we can try to catch high flows of people, and it's this kind of flows you want to catch with public transportation. So we kept the 7 hours represented here. So this is the mobility according to the different hours of the day, so we can see both peaks to go back and from to go to and from work. Then we wanted to keep, high flows in times, but also people going along the same roads, because you can have a massive departure at a given time, but in any direction, so that it's not interesting to have public transportation. So we need to catch the flows that are going along the same roads. And here we studied where people live and where people work in order to see what was the patterns of flows. And it's actually for every conurbation in France, it's very radial. Here is for Île-de-France. We assume that only car mobility could be cut by the buses or trains. This is an assumption. We also needed to check that people were not living too far from train stations and or highways. So here, actually, what you can see on those maps is the location of train stations on the bottom figure, and of highways on the upper figure. And what you can see, I just drew 5 kilometer circles around those stations or highways, and it pretty much covers 100% of medium density areas in France. Then we allocated the trips according to if people were living closer to highways or closer to train stations. And there was a last criterion about the distance of the trip, because if the trip is too short, actually it's a hassle to go to the station, wait for the bus or the train, and then interconnect to take urban modes. You just keep taking your car. So there was a distance criterion, and the trips needed to be long enough in order to be allocated to bus or train. And here is a summary of our hypothesis. We had hypothesis about the average emissions of buses and the average emissions of trains. And it gives these results. I'm going fast, but it's a 8% reduction in CO2 emissions, even though the traffic is actually reduced by 14% because buses and trains also emit CO2. So you have it decreases the result compared to traffic reduction. And last, ride sharing. So here the system that we imagine for ride sharing is based on two different kinds of communities. So you can share your rides with your work community, so with your colleagues, or you can share your rides with the people living in the same commune as you for all the other motives. We assume that all the chain trips were excluded from carpooling for organizational reasons. In the max potential scenarios, we assume that everybody was willing to ride share, no matter of the trip distance, no matter of the sociology of the people, no matter of if they have a car or not, etc. Whereas in the ambitious scenario, we asked experts to assess the probability of those trips to be carpooled or not. Then we had a 30-minute time flexibility assumption, meaning that people were willing to delay their departure by 30 minutes in order to arrange a share. And finally, we had this maximal detour assumption for the driver. So the driver could not do a detour of more than 10% of the total distance of his trip in order to pick up the passengers. So here is how we interconnected all the assumptions. It's kind of complicated, but we have the upper part trying to assess the share of trips that could be carpooled. So all the other trips which are not in this share cannot be carpooled, and their occupancy rate remains the same. For the share that can be carpooled, we then needed to compute the increase of occupancy rate thanks to car sharing. And as you know, the more trips you can share, the easier it is to find a carpooler. So there is a double effect of this size of trip community that you can share. Yes, and for the geographical check, we used also a Monte Carlo simulation, which was based on this carpooling angle. So here you can imagine that the destination of the trip is at the center. The origins of the trip are the blue dots, and you have this carpooling angle representing the 10% maximal detour of the driver. And if two blue dots are actually in the angle, you imagine that the trips can be shared in the same car up to 4 persons per car. And as you can see, the more trips you can share, of course, the easier it is to share rides. And so here is the plot of the occupancy rate of cars given as a function of the number of trips that you can share at a given moment in time and in space. And here you have the sensitivity of the carpooling angles, and which shows the 10% maximal detour, which is the red curve. So what you can see is that above 400 trips to share, all the cars are full. So if at one moment you have a community of trips of more than 400, you can fill up all your cars, basically. So we needed then to assess the size of the communities, etc. And we got a 41% increase of global occupancy rate for the max potential scenario, and a 7% increase of this occupancy rate for the ambitious scenario. So you see that there is a huge effect of the fact that there are filters about distances of trips that have been defined by the experts, the sociology of people, etc., so that it reduces the number of trips that you can share, and it reduces the easiness of finding carpoolers. And so it can be felt and seen in the CO2 emissions. The max potential scenario leads to a 27% reduction of emissions compared to the reference scenario. and for the ambitious scenario, you get a 6% reduction. So here is a synthesis of the different domains of action when you activate them one by one. So you can see that the bike and ride-sharing systems are the most promising one within this pool of different solutions. And the last question we wanted to answer was what happens if you activate all the different mobility systems at the same time instead of just activating the levers one by one. So when you try to answer these kind of questions, you have to handle the different interactions that will happen between the different levers. You can have positive interactions, meaning that you will decrease your CO2 emissions more when you activate both levers than the sum of activating one lever at a time. For example, if you activate bike system and telework, so for the telework system alone, you have telecenters everywhere, but maybe people will still go to the telecenters by car. So it just reduces the distance of the car trip. If you just have bike, all the trips that are far away for work cannot be done by bike, so you do it by car. But when you put them together, you can go by bike to the telecenter. So you further reduce CO2 emissions. You also have negative interactions, mostly because the basis of trips intersect between the different domains of actions. So for example, one trip can be teleworked or carpooled. So it can be teleworked in the telework scenario, it can be carpooled in the carpool scenario. When you activate both, you will not do both, right? So you need to define priorities between the domains of actions for those cases. And the priorities we defined here were following the avoid, shift, improve philosophy. So first, people in this model would try to avoid the trip thanks to telework or to grocery deliveries at home. Then they would try to go from a higher carbon mode to a lower carbon mode. So first to bike and then to public transportation. And then if you cannot do anything else and still use your car, you try to improve the occupancy rate of your car. There are also, so all the interactions I just talked about were included in the model, but there are interactions that we did not model, which are more linked to the lifestyle of people. Because if you activate all the levers at the same time, maybe car ownership is not interesting anymore because there are enough alternatives for people. So maybe people will sell their cars. And experiments show that it further reduces CO2 emissions because you actually relocalize your lifestyle so that you change your destinations. Actually, you try to find closer proximity shops, things like that. This effect is not taken into account. Another effect which is not taken into account is the rebound effect, because those alternatives cost less for people than owning a car, so they might increase their purchasing power and spend it in other more carbonized activities, so it's not taken into account in the model. Here is a summary of the hypothesis and the results. So on the upper left corner you can see the decrease in mobility thanks to telework and to grocery delivery. On the upper right you can see the modal shift, so more and more bicycle in orange, and for the max potential scenario at the right you can see the increase in public transportation. On the lower left you have the increase in occupancy rate within the car traffic, and the final results here about CO2 emissions. For the max potential scenario you have a reduction of 60% for daily mobility compared to the reference scenario, and in the ambitious scenario it's a reduction of 25% of CO2 emissions. Okay, I hope I showed you that there exist interesting alternatives to car, even in medium density areas. And I showed you some kind of quick and dirty models that I use to answer very specific questions. And as experts in modeling, if you have feedbacks or comments, I would be glad to answer. Thanks for your attention.
Thank you very much. And now we're open for discussion. Marie.
Thank you for this very interesting presentation. And it's just a comment because that kind of study leads us to think that we have to think more about how we organize cities and economic activities and dwelling, where they're located in France. We have to think back spatial planning, for example, where we live, and how local authorities handle these issues. Some things need to be changed as regard public policies, and this is important to have that kind of study to support this goal. Also, thank you.
Yes, yeah, definitely.
Thank you for your talk. I liked it also a lot. I have two comments. Did you only consider at the moment CO2? Did you also go into, for example, nanoparticles, small particles emitted? Because there it's also the big feature that in the first kilometer you have 100 times higher.
Sorry, I can't hear you.
Did you also take into account, besides CO2, also small particles, nanoparticles emission? And there is also the effect, I don't know whether you, that in the first kilometer, a normal car is emitting 100 times more nanoparticles. I think also CO2, it is a little bit dependent how far you are going, so that this is weighted. So if you take, for example, the bicycle for the short distances, that then proportion, not only the distance percentage, there's a bigger effect. And I have another point where you a little bit tendency, why did you show the sign of the bicycle always with a screwdriver?
With the?
Screwdriver.
Screwdriver. Ah, the. Where is it? Yeah, in clé anglaise. Ah, yeah, it's okay. Yeah, okay. It was to illustrate the services, because the bike system, is like infrastructures, vehicles, but also services, and so you need repair stations, etc. Yeah, okay. And for the first question, it has not been included in the model. We just included the effect of which kind of road you use. So if you have to stop often in dense urban areas, it's taken into account that you emit a bit more. But what you say about if effectively the amount of CO2 is greater at first kilometer, then it would further improve the results of bicycle. And the particles are not estimated in this study, but it would be interesting also to have such results.
Actually, I think he took into account the nanoparticles, which are the CO2. It's microparticle that you're taking. Yeah.
In your projection at the beginning, between now and 2026, in the mixed you presented, we have seen that gasoline is increasing, diesel is reducing.
Right.
But my question inside this gasoline, how much have you integrated 100% pure biogasoline, for example, and how much assume that at the end you have 10%, for example, how it will be important in comparison of the other cases you demonstrated? That means that everything being equal, toutes choses égales par ailleurs, how big will be the impact of, for example, 10%, 100% biogasoline on that?
Well, we have not run those simulations, and actually in the reference scenario, even in the reference scenario, I think there is no biofuel included, so 0. And so the question is, it was 100%, what would be the effect of it, right? I guess it depends on the way you produce your biofuel, and so the carbon assessment of this biofuel that you put in the engine. But yeah, it would be a question to ask in that case. Yes.
Yes.
Oui. Okay.
Thank you for the talk. I really enjoyed the detail of each section.
Yeah.
And that must have been a lot of work with different data sources. Maybe you had some problems to combine these different data sources.
Yes, sometimes.
Well, a few comments. First, on your main conclusion, you say the bike system and the ride sharing are the most have the most potential. Don't you think that you're talking about the max potential, not the ambitious, and the ride sharing is really extremely ambitious in terms of max potential? And if you look at the difference between the two,
yeah,
is huge. And
huge.
I wouldn't trust a second the max potential like everyone sharing car.
Yeah.
So for me, the conclusion is a bit biased on that point. Right. And so the bike system is really the biggest one. And could you also, I mean, just for me, you also show that telework is really kind of bullshit. And I mean, it's 1% in the ambitious. And also, I don't trust much the max potential. So it's a good result. I mean, because when you hear people talking about reduction of mobility and so on, the first thing they tell is telework. They don't talk much about bike, but when you show that, it's very good result. Another thing is for the delivery of goods. With all the data you have, would it be a lot of work to think the thing differently, like to bet on proximity shops? And so, I mean, myself, I have the food co-ops, and in the same city there are 3 now. It's spreading because people love it, and you can really walk there or bike. And then the optimization is about the delivery to these shops, and it's maybe more easy and more efficient to do that. Would it be something that you could do? And the last thing would be to think about the unemployment rate linked to the forced mobility. Like, I think if the unemployment rate is lower, you have the capacity to live closer to your work, because you can change work more easily, change your job.
Mm-hmm.
And in a very constrained, very high unemployment, even if you have a job, you find a job 80 kilometers, you take it, you know?
Mm-hmm.
So it would be interesting to think about the distance to work.
Okay, so 4 questions. The potential, the max potential for ride sharing, indeed is a max potential. But it's there are 2 things. You know, there is this sociology effect, like who is ride sharing, and also the motive. What do you want to go? Where do you want to go? And what do you want to do? What activity you want to access? And there is also the distance effect. So in the max potential, we assume that whatever the distance, the trip could be shared. So even if you do like 1 kilometer, you can still share a ride, which is actually a kind of weird assumption when you think about it. But if you mix both bike system and ride sharing, all these little trips will actually be performed by bike. So the interaction between both might actually sum up, right? Yes, so that was the first question. The second question about telework. Actually, yeah, the total potential is low, but you can still check at specific locations. Maybe it can be interesting locally, and maybe it's efficient locally, but you will not revolutionize mobility and CO2 emissions with this. You will rapidly reach the maximum of CO2 emissions. That's what it means. It doesn't mean you should not do that. It means that the potential is not so big. About so for the delivery rounds, what we did here is just replace hypermarket and supermarket. We did not consider proximity shops, so all the proximity shops are still the same. And what we thought about this delivery system was that people would have to wait 3 days every time they get delivered, so all the fresh food would actually be more bought in proximity shops. So actually this kind of system might influence people to go more to proximity shops and just get like the cereals, the milk, and your things that are toilet paper or whatever that are big groceries, and they are delivered only every 3 days. That might be an effect to favor more the proximity shops. And the fourth question, unemployment, that would be an effect that could be studied for sure. Yeah.
Yes. I think your bike estimation is a bit optimistic because you should consider
that's the max potential.
Yes, but even not the max potential, because if you should consider some topography effect. If you live in somewhere where you have big hills, it's more difficult to use bike, or you have a cutoff of the waiver.
The waiver?
The waiver. For example, if you go to south of France and you want to bike in the morning, it's okay. But if you go back in the afternoon when it's 40 degrees and with global warming it's getting more and more hot, you don't want to do it.
Yeah. Okay. Yeah, we did not take into account any of those effects. For the topography, with the help of electric bicycle, you really need like steep slopes before not being able to do it by bike. So this effect, I think, is reduced. For weather, we have the example of Netherlands, where the bad weather actually is not a problem, but with global warming and hot weather, it indeed might become a problem. But here again, the electric bike is like easy to activate, so you don't do much effort, but you don't have AC. That's for sure.
I have only 2 comments. Rain keeps you from bicycling. So, and in this winter, more than most people don't ride the bike, at least not if you have longer distance. In Amsterdam they do, because there's almost no other way to do it. But otherwise, I think in the summertime this is a good object, but in the wintertime, with ice and snow and rain, so you have almost half a year cut out of the bike system.
Yeah, for sure. For snow and for really
and
hot weather, there are limitations.
With the shops nearby, our shop just closed down because the bigger markets are cheaper, and people prefer to ride their car to buy it cheaper.
Yes.
And and especially the fresh things you don't get at a small market, because it's so difficult for them to handle that.
Yeah, for this delivery round system, we actually could not figure out an easy way to organize this kind of things. And so that's why we just have a max potential estimation, because we figured out that it would be very difficult with policies or whatever to organize such a system. So it's not really realistic.
Did you think about delivery by what is the word?
Rounds, delivery rounds.
A little Zoom.
Drones.
Drones. That's what Amazon is planning.
No, actually,
with fresh food too.
Yeah, Amazon is trying to do that. Well, in terms of energy, it would be far less efficient for sure in terms of CO2, so it depends on how you produce your electricity. But we did not consider this option.
Another question? Last one, maybe?
Another general question is that those results on the blackboard are not normalized through economy, because some can have a positive effect on economy and some can have a negative effect on economy. So in order to compare that on a more arm's length basis, it should be normalized through economy impact.
Yeah, we estimated the impact, like the cost of those different systems. So for most of them, actually, what you see is that the money that you have to invest in the infrastructures or the vehicles or like in the system is more than compensated by the reduction in fuel imported and in car manufacturing. Because you use your car less, so it remains a bit longer in the stock, so you have to change it less often, and these both effects actually often, for most of these domains of action, counterbalance the investment that you have to put in them.
Thank you, Clémence. I also worked with Nicolas on this project. I just wanted to respond to Jürgen just to precise something. It's that in the hypothesis for these models, we have incentives. So that means that people actually will want to take their car less because it costs more. That's one of the big hypotheses. That's why they would also take more the bike and try to use other alternatives. It's not just on their own will to do it. It actually is an economical choice. Probably that's the idea.
But our main supermarket now in this whole area, they have reduced their bike racks again and opened only parking lots because people in the winter don't buy, and even the shops want big things to buy, and you can carry big things, and you don't drive there for little things. So most people in our neighborhood, they shut down our neighborhood shops. Everybody says, no, we go rather to the car because we need to buy a lot of things.
Yes, so far, but the idea is to change that, because if you make fuel more expensive, then all of these things must change.
Yeah,
and
apparently people don't think that way at the moment.
Not at the moment.
Yeah, we are trying to do that, but we lost because we were very hard in favor of keeping this shop. But we lost, and the majority said no.
Yes, we need political will in order to implement those systems.
Thank you. Just